Today I will present the general methodology for the uncertainty quantification of the occurrence of different bifurcation types in random ordinary differential equations. So let me say that this is joint work together with Kerstin Kuehn from the Technical University of Munich. So as many of you as well in this mini symposium, I'm part of the TPAS project, which is Tipping Points in the Earth System, which is a project funded by the European Union's Horizon 2020 Research and Innovation Program. So many real-world phenomena can be modeled by a system of nonlinear ordinary differential equations. So for the talk here, we consider a system of these equations given by x dot equals f of xr, where f is a smooth vector field and r are the corresponding parameters. And then there is a vast amount of literature, and we can build upon a well-developed classical bifurcation analysis. And for these systems, you can calculate the stability properties of equilibria, and you can determine the precise bifurcation type that is inherent in the system. So whether the system is subcritical, has a subcritical bifurcation or a supercritical one. And this is important because you already heard about the tipping phenomenon in the first talk of Niklas, how this works. And the link here is that a tipping point is actually a subcritical bifurcation point. So now I'd like to invite you to think about your favorite real-world phenomenon and the corresponding dynamical system. So if you have that in mind, it might well be that there are a number of parameters appearing in this system. And if not, just think about some savanna ecosystems or a model for the firing of neurons where you clearly have these parameters. And the question now is, do we really know exact values for all these parameters? Or is it rather a range where you would expect these parameters to be inside? And if the latter is the case, we no longer deal with a deterministic quantity, but with random variables. And the research question I brought for you today is, how does this parameter uncertainty affect the bifurcation behavior of the system? And as we are here in the mini symposium on tipping points in natural system, it's particularly interesting to really calculate the probability of an inherent tipping point in the system. So that's what we're going to do now. I will start with the general methodology and the system reduction. And then the main focus of the talk will be about the bifurcation normal form coefficient, and especially on its probabilistic analysis. And for this, I brought two approaches, an analytical one and a semi-analytical one. And I will conclude my talk with a short summary and outlook. So the research question for today is, what is the probability of an inherent tipping point so that we face a subcritical bifurcation? Think about a climate model with many unknown parameters. What you do have are measurements, for example, like temperature or salinity data. And from that, you could solve an inverse problem of parameter fitting, and you might come up with a climate model with uncertain parameters and their probability distributions. This model might still be very large and not that handy for a probabilistic analysis, and that's why it's really convenient to first have a reduction step and to reduce the system to some kind of reduced climate dynamics where you still have the important qualitative behavior of your system. So that would be the first step. And then with these reduced climate dynamics, you can perform a probabilistic analysis to really calculate the probability of an inherent subcritical bifurcation. And for the talk today, I would really like to focus on the lower part of this big picture. So we're going to perform two steps, where the first one is the reduction step. And the second one, which is the main focus of the talk, will be the probabilistic analysis of the arising bifurcation normal form coefficient. So for the first step, the reduction step, I brought a famous example for you, the Lorentz system, which is a model for fluid convection. And you can see it here. It consists of the system of three ordinary differential equations, where R1 and R2 are now absolutely continuous independent random variables on a probability space omega script AP. Rho is the bifurcation parameter, and X, Y, Z is an element of R3. And as many of you know, you might apply the famous center manifold theorem to obtain the reduced dynamics of this Lorentz system on the center manifold in a normal form given by this equation for u dot. And if you have a closer look at this equation u dot, you can recognize that this equation is the normal form of a pitchfork bifurcation. And for our talk, it's important to determine the precise type of this pitchfork bifurcation. So a subcritical one would be linked to a tipping point, whereas a supercritical one would be linked to a rather smooth transition in the system. And whether it's sub or supercritical depends on the sign of the so-called bifurcation normal form coefficient. And this is this quantity that I denoted here by capital X, which you can see is a nonlinear function of the two input parameters R1 and R2. And this is the most important quantity for the remainder of the talk, because the sign of this bifurcation normal form coefficient determines whether we face a super or a subcritical bifurcation. So we have performed the first step, and we now have our bifurcation normal form coefficient at hand, and we can come to the probabilistic analysis of the reduced system. So the goal is to analyze this general nonlinear function g. It does not have to have a particular shape, but it's a really general nonlinear function of the uncertain input parameters R1 to Rd. And the challenge thereby is that the probability distribution of X is difficult to calculate because it's given as this nonlinear transformation of the random input parameters. And Kerstin, Kuehn and I came up with 3 approaches to calculate the probability distribution of this X. The first one is an analytical approach. The second one is semi-analytical one. And we also have an approach based on the uncentered transformation. For the talk today, I'd like to focus on the first 2 of these. And you can find further details in our current preprint, which you can find on arXiv. So let's have a look at the analytical approach. So imagine this bifurcation coefficient X, and if it was just the sum of 2 random variables, we could easily employ the classical convolution formula to obtain its probability density. But as it is a nonlinear, general nonlinear function, you have also to deal with products in this coefficient, and there this no longer applies. And for these products, there is a nice integral transform known from classical analysis, which is called the Mellin transform. And this is a nice tool to handle these products in the bifurcation normal form coefficient. It's defined, the Mellin transform of f is defined as the integral over the positive half line of x to the power of s minus 1 times f of x integrated with respect to x. And this is for a single real valued function f, which is defined almost everywhere for positive x. And as you know from the Laplace transform, there's also an inverse transform linked to this integral transform. It's called the inverse Mellin transform, and it's given by this weighted complex valued integral here. And if the existence of the Mellin transform is ensured, and the Mellin transform itself is an analytic function of the complex variable s, where its real part is bounded between 2 real constants, C1 and C2, you can really define this inverse of the function and you get back the probability density. And now you might ask, how does this Mellin transform actually help us to calculate the probability of a subcritical bifurcation? And here's the nice link, because there is a probabilistic interpretation of this Mellin transform. So imagine you are giving a random variable xi, almost surely positive, with corresponding density rho xi of x. And if you calculate the Mellin transform of the probability density, you recognize that it's the expected value of xi to the power of s minus 1. And I mentioned that it's very helpful to calculate probability densities of products, and here is why. If you have 2 positive independent random variables having probability density functions rho r1 and rho r2, these can then be, the product density can then be expressed as a Mellin convolution. This you can find in a book of Springer from 1979. And you have this nice analytical formula for the product density. So let's have a concrete example for this. So imagine I give you the reduced dynamics that you can see here. So we already have performed our first step, the reduction step, and we already have the reduced dynamics. And for this, we now do the probabilistic analysis of the bifurcation coefficient minus R1 times R2. So this in front of the cubic term. And it's well known that if it's larger than 0, you face a subcritical bifurcation. If it's negative, you face a supercritical one. So assume now more concretely that R1 is uniformly distributed on -1 to 3, and R2 is gamma distributed with shape parameter 3 and weight 1. And those two variables should be independent. Some of you might have noticed that I actually said that it's for positive random variables, but there is a nice extension of the Mellon transform also attaining negative values in a paper of Epstein already in 1948. So we can also handle these two parameter distributions. And then the probability density of this bifurcation coefficient is easily calculated via the Mellon convolution. And for this formula here, I would just like you to note that we really have an analytical expression of the probability density of the bifurcation coefficient. And for our talk, it's important to know whether there is an inherent tipping point. And the probability for letter 1 is that this coefficient is positive, and in this case, it's 0.25. So now, think about these bifurcation normal form coefficients. It might well be that they have a by far more complicated shape than just the product of two random variables. And therefore, this analytical procedure might no longer be applicable. So that brings me to the semi-analytical approach. Our goal is to carry over as many benefits of this analytical approach, because it's nice we do not induce any error because we have an analytical calculation of the probability density, and we want to keep as much as possible. So the idea is to decompose the bifurcation coefficient in an analytically tractable part and a non-tractable part. So think of the first example that I gave you, the Lorentz system, where the bifurcation normal form coefficient has this particular form. And if we now calculate its Mellon transform, you can decompose it in the product of the blue and the red part, where the blue part is analytically tractable because of operational properties of this integral transform, whereas the red one is not. So we have to somehow handle this. And for this, I brought for the remainder of the talk 3 questions for you, where the first one is, what is the Mellon transform of the part containing R1, so the red part? We have to somehow deal with that. Then what is the Mellon transform of the complete bifurcation normal form coefficient? And then finally, the main question, what is the probability for the pitchfork bifurcation to be subcritical, to have an inherent tipping point? So let's start with the first one. We can combine the Mellon transform with the generalized polynomial chaos expansion. And it's well known that under suitable assumption, our nonlinear transformation G of R1 can be represented as the polynomial chaos expansion, the infinite sum of coefficients Gn times phi n of xi. And thereby phi n is the orthogonal polynomial basis, and xi is called the stochastic germ. Gn are the corresponding PCE coefficients. And as you might imagine, for numerical tractability, we work with a truncated version of this PCE. And furthermore, we collect powers of the stochastic germ so that we finally come up with an approximation of our nonlinear transformation in terms of this finite sum from n equal to 0 to capital N of Cn times xi to the power of n, where Cn are the coefficients calculated based on the collected powers of xi. And the nice thing now is that we can take into account the remaining analytically non-tractable combinations of input parameters via this polynomial chaos expansion. And this is because the stochastic germ xi usually has a standard distribution, like for example, uniform distribution. And the Mellon transform of xi is known in analytical form. For xi uniformly distributed on 0, 1, you can find again in this Epstein paper from 1948 that the Mellon transform of xi is just 1 over s, a very simple form, and we can deal with that. So far, we trace back the uncertainty from the complicated nonlinear transformation of R1 to the uncertainty of the stochastic germ psi. The problem that remains is that we have a sum of powers of psi. In general, we know that the Mellin transform of the sum of two random variables is not equal to the sum of the individual Mellin transforms. A remedy to this is that we restrict our Mellin transform to integer values, and then we can use the binomial formula iteratively. And if we do so, remember this is the polynomial chaos expansion for G of R1. And if we calculate the Mellin transform, we come up with this expression on the right-hand side, where you really only have the individual Mellin transforms of the stochastic germ psi, which are very easy to calculate. And Ci hat here denotes just the cumulated coefficients for the different powers of psi. So we have solved our first question. What about the second one? So how can we glue together this Mellin transform of the red part to the one of the blue part, because we want to calculate the Mellin transform of the bifurcation coefficient. So to do so, we use again some operational properties of this integral transform that gives us that we can calculate the blue part as the Mellin transform of the second input parameter evaluated in -s+2. And again, here you really have only the Mellin transform of this individual parameter. Then we can combine the blue and the red part to finally obtain for the Mellin transform of the complete bifurcation coefficient this product here, where I really like you to note that we only have Mellin transforms of the individual parameters here inside, so of R2 and the stochastic germ psi that we use to approximate R1. And this is the main insight. But now still, I gave you now the Mellin transform of the bifurcation coefficient, but what we are actually interested in is the probability of a subcritical pitchfork bifurcation. So this brings me to the last question for today. How can we get back to a probability? And for this, we first have to note that we can no longer simply apply the inverse Mellin transform, because remember, we restricted ourselves to integer values of S. And there I'd like to remind you at the beginning of the presentation, where we have recognized that the interpretation of the Mellin transform is that it is the S-1th moment of the almost surely positive random variable psi. And moments are available in closed form without sampling with these techniques, which is really nice, because we came from this general nonlinear input, this general nonlinear transformation of the input parameters now to their moments already. And what remains to do is the approximation of the probability density function rho x of our bifurcation normal form coefficient from this series of moments. And for this, we used a Gaussian mixture model. You can find more details in a paper of McLachlan and co-authors. And this is an approximation where you approximate the probability density function of x by a sum over component probability density functions, which are normally distributed with corresponding weights pi. And think of this as a very general approximation possibility. So when it comes to the estimation of probability density, this is, some people consider this somewhat as the replacement of a sigmoidal neural network, because it's a very general way of approximating probability density functions. And what remains to do in our case is we need to identify the parameters eta of this Gaussian mixture model. And we decided to do this via the generalized method of moments. And you can find details on that in a paper of Hansen from 2008. And this seemed natural, somehow natural to us, because remember, we have these moments of the bifurcation normal form coefficient in closed form. So therefore, we used the generalized method of moments. So for the last part of the presentation, I'd like to show you some numerical results that we came up for the Lorentz system. So we have solved all these three questions that I posed to you, and now we can actually show what the probability for the pitchfork bifurcation to be subcritical looks like. So remember the Lorentz system from the very beginning. And as said, the most important point is that now we have parameter distributions. So we assume R1 to be generalized beta distributed on the compact interval from -0.5 to 0.5 with parameters 2 and 5. And R2 to be gamma distributed with shape parameter 8 and rate 1. And if we combine this and really estimate our Gaussian mixture model, we come up with the following approximation of the probability density function of the bifurcation normal form coefficient, which you can see here in turquoise. And I marked the origin with the black vertical line because we are interested in the sign of this bifurcation coefficient. And we can then calculate the probability. Now you could ask, how good is this approximation? So how well are we doing? For this, I brought another approximation method for you. So it's implemented already in MATLAB, and it's the expectation maximization algorithm, which is also used to fit a Gaussian mixture model. And you can see it here as the magenta line, which is well in the range where we also are with our Mellon-based method. And we can put it even more simple. I also have just a plain vanilla Monte Carlo simulation, and the normalized histogram you can see in blue, which is again well in the range that we obtain. Now we are interested in this concrete probability. So let's have a look at the cumulative distribution function. And you can see here from this diagram that we can read that we obtain a probability for the subcritical pitchfork bifurcation with our method to be 0.9049. And for the plain vanilla Monte Carlo approach and for the expectation maximization, numbers are well in range. And with that, I already come to the conclusion of my talk. And I really would like you to remember basically two things of the talk. So the first one would be that parameter uncertainty can really crucially affect the bifurcation behavior, especially the precise bifurcation type. So remember, for identifying systems that are at risk of tipping, we need to find out what is the probability to really have an inherent tipping point. And the second point I'd like you to remember is that uncertainty propagation under nonlinear dynamics really induces the need for problem-specific tools, because this bifurcation normal form coefficient can take a wide variety of concrete functional forms. And today I presented two approaches, the first one being the analytical approach, where you do not need any sampling at all, and it's an exact method. The drawback, however, is that it's only applicable for simple structures of this bifurcation coefficient. And we tackled this by coming up with our second approach, the semi-analytical one. And again, the very nice thing is that you do not need any Monte Carlo sampling at all, and it's a very generic approach. However, you induce an error because you have the truncation of the polynomial chaos expansion, and of course, via the approximation by a Gaussian mixture model. But we have seen that it performs reasonably well. So for future work or ongoing work, we are interested in using real climate data to solve an inverse problem to obtain the model parameters for this climate model. So if you let me go back to my big picture slide, that would be the upper part of this slide. So we focused on this talk on the lower part, but it would also be interesting to not just assume some probability distribution, but really to infer these probability distributions from climate data. And of course, we are also interested on applying our uncertainty quantification method to further concrete climate models. And there I would be really happy to have your input if you have some models in mind where such an uncertainty quantification of the bifurcation type could be of interest. And with that, I'd like to conclude and thank you very much for your attention.